Welcome. Today we will see remaining part of the spur gear, that is estimation of module based on beam strength. Then we will see wear strength, and then we will see estimation of module based on wear strength. Now first point, that is estimation of module based on beam strength. We know that in order to avoid failure of gear tooth due to bending, beam strength should be greater than effective force. Therefore SB should be greater than P effective. Therefore, introducing a factor of safety, SB is equal to P effective into factor of safety. Consider this as equation A. The recommended factor of safety is from 1.5 to 2. The tangential component is given by Pt is equal to 2mt divided by d dash, where mt is equal to torque transmitted, d dash is the pitch circle diameter. Therefore, substituting the values, Pt is equal to 2mt divided by mz. Therefore, Pt is equal to 2mz into bracket 16 to 10 raised to 6 into kilowatt divided by 2 pi n, where small n is nothing but speed in RPM. Now we know that P effective is equal to Cs Pt upon Cv. Therefore, substituting the values of Pt, therefore P effective is equal to 16 to 10 raised to 6 divided by pi into bracket kilowatt into Cs divided by mzn into Cv. We know that SB is equal to mb sigma b into y. Therefore SB is equal to m square into b divided by m into SUT divided by 3 into y. What we have done, we have multiplied and divided by m, and we have written sigma b is equal to SUT divided by 3. Therefore consider this as equation C. Therefore from equations A, B and C we are getting module m is equal to 16 to 10 raised to 6 divided by pi into bracket kilowatt into Cs into Fs divided by Zn Cv into b divided by m into SUT divided by 3 into y bracket raised to 1 by 3. This equation is used in the preliminary stages of gear design. Now we will see wear strength of gear tooth. The failure of the gear tooth due to pitting occurs when the contact stresses between two meshing teeth exceed the surface endurance strength of the material. Pitting is a surface fatigue failure characterized by small pits on the surface of the gear tooth. In order to avoid this type of failure, the proportions of the gear tooth and surface properties such as surface hardness should be selected in such a way that the wear strength of the gear tooth is more than the effective load between the meshing teeth. The analysis of wear strength was done by Earle Buckingham in his paper The Relation of Load to Wear of Gear Teeth, which was submitted before the American Gear Manufacturing Association, that is AGMA, in 1926. Buckingham's equation gives the wear strength of the gear tooth. Buckingham's equation is based on Hurd's theory of contact stresses. When two cylinders are pressed together as shown in figure A, this is the figure A. These two gears are considered as two cylinders. The contact stress is given by sigma C is equal to 2P divided by pi BL, where B is equal to into bracket 2P into 1 minus mu square into 1 upon E1 plus 1 upon E2 divided by pi L into bracket 1 upon D1 plus 1 upon D2 whole bracket raised to 1 by 2. Consider this as equation B, where sigma C is equal to maximum value of the compressive stress in Newton per mm square. Capital P is equal to force pressing the two cylinders together in Newton. Small b is equal to half width of deformation in mm. L is equal to axial length of the cylinder in mm. D1, D2 is equal to diameters of the two cylinders in mm. E1, E2 is equal to moduli of elasticity of two cylinder materials in Newton per m square, and mu is equal to Poisson's ratio. Due to deformation under the action of load P, a rectangular surface of width 2b and length L is formed between the two cylinders. The elliptical stress distribution across the width 2b is shown in figure B and C. That is, this is elliptical stress distribution between the two cylinders. Substituting equation B in equation A and squaring both sides, we get sigma c square is equal to 1 divided by pi into bracket 1 minus mu square divided into P divided by L into bracket 1 upon R1 plus 1 upon R2 divided by 1 upon E1 plus 1 upon E2, where R1 and R2 are the radii of two cylinders. Substituting mu is equal to 0.3, we are getting sigma c square is equal to 0.35 into P divided by L into bracket 1 upon R1 plus 1 upon R2 divided by 1 upon E1 plus 1 upon E2, equation D. The above equation of the contact stress is based on the following assumptions. First, the cylinders are made of isotropic materials. Second, the elastic limit of the material is not exceeded. Third, the dimensions R1, R2 are very large when compared to the width 2b of the deformation. Figure shows the contact between the two meshing teeth at the pitch point. This is the figure. This is the pinion, this is the gear, this is the pitch point P. The radii R1 and R2 in equation D are to be replaced by the radii of curvature at the pitch point. Therefore, this R1 and this is R2, this is R1 and this is R2. Therefore, R1 is equal to dp dash sin alpha divided by 2 and R2 is equal to dg dash sin alpha divided by 2, where dp dash and dg dash are pitch circle diameters of the pinion and gear. Alpha is the pressure angle. There are two reasons for taking the radii of curvature at the pitch point. The wear on the gear tooth generally occurs at or near the pitch point. When only one pair of teeth carries the entire load, the contact occurs at the pitch point. When the contact takes place at the top or at the bottom of the tooth profile, usually two pairs of meshing teeth share the load. The dynamic load is imposed on the gear tooth near the pitch line area. Therefore, it is more reasonable to select the radii of curvature at the pitch point. Therefore, 1 upon R1 plus 1 upon R2 is equal to 2 divided by sin alpha into bracket 1 upon dp dash plus 1 upon dg dash, equation E. A ratio factor Q is defined as Q is equal to 2Zg divided by Zg plus Zp, where Zg and Zp are the number of teeth on gear and pinion respectively. Therefore, substituting dp dash is equal to mzg and dg dash is equal to mj, dp dash is equal to mzp and dg dash is equal to mzg, we are getting Q is equal to 2 dg dash divided by dg dash plus dp dash, equation F. Therefore, 1 upon dp dash plus 1 upon dg dash is equal to dp dash plus dg dash divided by dp dash d into dg dash is equal to 2 into 2 divided by capital Q into dp dash, equation G. From equation E and G, we are getting 1 upon R1 plus 1 upon R2 is equal to 4 divided by Q dp dash sin alpha, equation H. The force acting along the pitch line in figure is Pn. Therefore, P is equal to Pn is equal to Pt divided by cos alpha, equation J. The axial length of the gears is the face width V, that is L is equal to B, equation K. Substituting equations H, J and K in equation D. Therefore, sigma c square is equal to 1.4 Pt divided by Bq dp dash sin alpha cos alpha into 1 upon E1 plus 1 upon E2, equation L. This is equation 1. A load stress factor K is defined as K is equal to sigma c square sin alpha cos alpha into 1 upon E1 plus 1 upon E2 divided by 1.4, equation L. Substituting the above equation in equation L, therefore we are getting Pt is equal to Bq dp dash K, equation M. This equation gives a relationship between the tangential force Pt and the corresponding contact stress sigma c or k. When the tangential force is increased, the contact stress also increases. Pitting occurs when the contact stress reaches the magnitude of the surface endurance strength. The corresponding value of Pt is called wear strength. Therefore, the wear strength is the maximum value of the tangential force that the tooth can transmit without pitting failure. Therefore, replacing Pt by Sw, equation M is written as Sw is equal to Bq dp dash k, equation 2, where Sw is equal to wear strength of the gear tooth in Newton. Sigma c is equal to surface endurance strength of the material in Newton per m square. Equation 2 is known as Buckinghams equation for wear. The ratio factor for internal gears is defined as Q is equal to 2Zg divided by Zg minus Zp. The expression for the load stress factor K can be simplified when both the gears are made of steel material with a 20-degree pressure angle. In this special case, E1 is equal to E2 is equal to 2.06 into 10 raised to 5 Newton per mm square and alpha is equal to 20 degree. According to G. Neyman, sigma c is equal to 0.27 into Bhn kgf per m square, which is converted into Newton per m square, that is equal to 0.27 into 9.81 into Bhn. This value is in Newton per m square, where Bhn is the Brinell hardness number. Therefore, K is equal to sigma c square sin alpha cos alpha into 1 upon E1 plus 1 upon 2 divided by 1.4. Therefore, substituting the values, which is equal to 0.27 into 9.81 bracket square into Bhn square into sin 20 cos 20 into 2 divided by 2.06 into 10 to 5 divided by 1.4, which is equal to 0.156 into Bhn divided by 100 bracket square, which is equal to, therefore K is equal to 0.16. This 0.156 is converted into 0.16 Bhn divided by 100 bracket square, equation 3. The above equation 3 is applicable only when both the gears are made of steel with a 20-degree pressure angle. In other cases, equation 1 should be used. In order to avoid failure of the gear tooth due to fitting, the wear strength should be more than the effective force between the meshing teeth. Table 1 gives the material properties for the calculation. That is table 1, values of modulus of elasticity and Poisson's ratio for gear materials. Different materials are there: steel, cast iron, spiral cast iron, cast tin bronze, grey cast iron. For respective materials, these models of elasticity and Poisson's ratios are given. Now, estimation of module based on wear strength. In order to avoid failure of gear tooth due to pitting, we know that SW should be greater than P effective. That is, wear strength should be greater than P effective. Therefore, introducing a factor of safety, SW is equal to P effective into factor of safety, equation A. The recommended factor of safety is from 1.5 to 2. Therefore, we know that the effective load is given by P effective is equal to 16 to 10 to 6 divided by pi into bracket kilowatt into CS divided by mzn into CV, equation B. Therefore, we know that SW is equal to BQ dP dash K, which is equal to B, which is equal to M into B divided by M into Q into MZ into K. We have multiplied and divided by M. Therefore, SW is equal to M square into B divided by M into Q into ZP into K, equation C. Therefore, substituting equation B and C in equation A, we are getting M is equal to 60 into 10 raised to 6 divided by pi into bracket kilowatt into CS into Fs divided by ZP square into NP into CV into B divided by M into Q into K whole bracket raised to 1 by 3. Therefore, this equation gives the module based on wear strength. Thank you very much. This is the end of the chapter spur gear.